In the second module of contingency table analysis, I am going to show different inferential statistics related to the contingency table analysis, how that need to be applied through our statistical software. I start with a cross-tab function that is actually a function that can generate the table just like SAS or SPSS outcome along with the chi-square value. And then we'll see how the chi-square test of independence can be applied here through R, and then Fisher exact test, and then finally we'll look for different kind of association. Phi contingency coefficient, the contingency coefficient, Kamer's V coefficient, and then we'll see the degree of agreement in R, how it need to be implemented here in R, and then different plots that would be very relevant for the degree of agreements. And then these are the few different functions that we are going to use, that available function from R, and different softwares that different packages of R that are available, say for example VCD and VCD extra. This is mainly these two packages we'll use, and we'll also use the CA package for the correspondence analysis, and there are some correspondence plots would be available, some functions. So we'll use that function to get the plot a visual impression of that analysis through the dimension plotting dimension 2 against dimension 1. And this all about the different inferential aspects of a contingency table that we are going to learn today. Let's go back to the presentation, how I have arranged for you. Let's see. In the second module of categorical data analysis, or rather the contingency table analysis, we will mainly focus on the inferential part. First we'll start with a tabular display. It's like SAS and SPSS, the way those two software displayed. R also can do this by the help of the package, the G models. So first we'll start with the cross table. The cross table is a function available in G models that is two-way cross tabulations. It gives you just like the SPSS or SAS output. So first I load the library G models. If you don't have, just install it from the CRAN and then load it, and VCD extra that already I talked about the previous module, and GS tab data that we already used before. So I'm taking the GS tab data here, and the cross table. To use the cross table, you just write the GS table, the X tables that we have generated. That object has to be should be the first argument of cross table. Then prop.test equals to false. Prop.t equals to the total proportion, the prop.r the row proportion, the prop.c that the column proportion. Initially I'm setting as false just to make the table dimensions a little low, and that you can see the results as that here the chi-square contribution is the n, and then total observation in table 980, and then all table wise all values are given here. This is the frequency, as a chi-square value. All different. If you say the total is required, then prop total is true, prop R is true, prop.c is true, then you will get all the informations one by one within this shell. In details I cannot display here in this PPT, but you can try it. You can take the help of cross table documentations that might give you better clarity. This is something that I copied from the cross tab documentations for your understanding. The arguments that you need to pass through are one of that is X, the vector of matrix. If Y is specified, X must be a vector, and Y a vector in a matrix or a data frame. And digits, the number of digits after the decimal point of the cell proportion. So proportions, what would be the significant digit that need to be displayed? The maximum width in case 1 by n table, default will be to print the outcome horizontally. If the number of columns exceed maximum width, the table will be wrapped from each successive increment of maximum dot width columns. Expected, if true, then chi-square will be set to true and expected cell counts from the chi-square will be included. Prop.r, if true, then row proportion will be included. Prop.c, if true, then column proportion will be included, and prop.t, if true, the table proportion will be included. The prop.chi-square, if true, the chi-square contribution of each cell will be included. Chi-square, if true, the results of chi-square test will be included. Fisher, if Fisher is true, then it would be Fisher, the results of Fisher exact test would be included. And McNamara, if is true, the results of McNamara test will be included. McNamara for the repeated measure design for a categorical data. And say reside, if true, then the residual will be included. Then S reside, if true, the standardized residual will be included. If A as reside, if that means if true, then adjusted standardized residual will be included. Missing dot include, if true, then remove any unused factor levels. And format either SAS or SPSS depends on the type of outcome desired, whichever you want. The format to default is SAS, and second format like SPSS you can get it. And DNN is the name to be given in the dimension in the results. That is the dimension names, and three triple dot options are there for any other arguments for any functions that you're using in between. And so for further details, as I mentioned, see the help of cross table, might give you much better clarity. Lot of examples are there. You can copy and paste in our console and run them, and can see what's the outcome that it has been generating along with the different inferential statistics. Next, we will move to test of independence, the chi-square test. Start with the chi-square test. For two-way tables, you can use chi-square.test function to test independence of row and column variables. By default, the p-value is calculated from the asymptotic chi-square distribution of test statistics. Optionally, the p-value can be derived via Monte Carlo simulations that you can mention there while you are calling that function. For example, suppose here I data that we used in the previous module that can be called here, and the margin dot table here I column 1 and 2, then you will get the table as this. It was the here and I would be there, the gender would be removed, so gender would be summarized. So now we make that here I three-way table into two-way table by summing up the gender information. Then the chi-square dot test, that here I can be passed through the chi-square dash test, and that it will give you the chi-square value, the degrees of freedom, and the p-value. And p-value, as you can see, it's much lower, so it is statistically significant. Next, we move to Fisher exact test. The Fisher dot test provides an exact test of independence. X must be a two-way contingency table in the table form. Another form, the Fisher dot text x comma y takes two categorical vectors of the same length. Two-way you can use this particular function. For example, suppose the larger than 2 by 2 methods can be computationally intensive if the frequencies are not small. And here the Fisher dot test, I am passing the GSS tab, that earlier data, and that will give you the Fisher's exact test results as the p-value and two-sided test. The p-value is showing it is significant. The Mantel-Hassel test and the conditional association in R. Use the Mantel-Hassel test by the function Mantel-Hain dot test function to perform a Cochrane-Mantel-Hassel chi-square test of null hypothesis. The two nominal variables are conditionally independent in this form. Say A is depends on B given C. In each column, if A is perpendicular to B given C, in each strata, assuming that there is no three-way interactions. If X is a three-dimensional contingency table where last dimension refer to the strata, consider UCB admission data where there is a 2 by 2 by 6 table with department as the stratified factor. So you can use that data for a just to get the idea about the data. You just type UCB admissions, that will give you the structure of the data that enter here. Now you just pass that UCB data admissions object through the Mantel-Hain.test function, and that will give you the Mantel-Hassel chi-square value, degrees of freedom, and p-value, along with the 95% confidence interval of the odd ratios and the common odd ratios. If normally if Mantel-Hassel test showing that it is not significant, if it is significant, that means they are significantly different, but if they are not significant, that means they are same. So you can combine the two odd ratio and can show the common odd ratio. So common odd ratio also would be displayed here by these particular functions. The results show no evidence of association between admission and gender when adjusted for department. However, we can easily see that the assumptions of equal association across the strata is probably violated. For 2 by 2 by k tables, these can be examined from odd ratios of each 2 by 2 table and tested by the Wolf_test function in VCT. Suppose the odd ratio of that UCB admission data, if you ask for, then it will give you the list of all odd ratios here, and then what you can do, you can just say LOR, then odd ratio UCB admission, capture the log odds ratio, and then summary of LOR is like this. So this is the summary, and then Wolf_test UCB admission, if you pass through, then it will say that P is 0.030. So that means they are significantly different, they are not same. We can visualize the odd ratio of admission for each department with the fourfold display, using very useful display, using fourfold functions. The cell frequency Nij of each 2 by 2 table are shown as a quarter circle whose radius is proportional to square root of Nij, so that its area is proportional to the cell frequency. Confidence rings for the odd ratio allow a visual test of null of no association. The rings for adjacent quadrants overlap if and only if the observed counts are consistent with the null hypothesis. In the extended version, the brighter color are used when the odd ratio is significantly different from 1. If you see this example, a fourfold is a function, and then UCB admission data been passed, and MF row 2 by 2 by 3, total 6 would be there. So 6 plots in 2 by 3 format that we are displaying, and color equals to that color specified at the top of the fourfold functions that I used, and then it will be displayed in this manner. If you see the first plot, this one, that actually that confidence rings are not at all overlapping. So here the odd ratios are different, but other cases, most of the cases, you will see that the 4 quadrants confidence rings are actually overlapping, so they are not statistically significant. So another VCD function that is quotable plot provides a more general approach to visualize the conditional association in contingency table, similar to trellis-like plots produced by coplot and lattice graphics. The panel argument supplies a function used to render each conditional subtable. The following gives a display similar to the previous figure. Say quotable plot UCB admission panel equals to quotable underscore fourfold, and that will give is almost similar what we got by the fourfold functions that we used. The Cochrane-Mantel-Hazel test for ordinal data. The standard chi-square test for association in two-way table treat both table factors as nominal or unordered categories. When one or both factors of two-way table are quantitative or ordinal, the more powerful test of association may be obtained by taking ordinality into account. Using row and column scores to test for linear trend or difference in row or column means. More general version of CMH test are provided by assigning a numerical score to the row and column, equidistant score that can be assigned. For example, with two ordinal factors, say R and C, we can assign the score for row 1 to R and for column 1 to C, where R rows and R columns are available in the table. This is statistically equivalent to Pearson correlations between the inter-score table variables for chi-square with chi-square n-1 R square with only 1 degrees of freedom, rather R-1 into C-1 for the test of general association. When only one table variable is ordinal, these general CMH tests are analogous to an ANOVA. The testing whether the row mean score or column mean scores are equal, again consuming fewer degrees of freedom than the test of general association. The CMH test function in VCD Extra now calculates these various CMH tests for two possible order factors, optionally stratified other factors. Let's consider the following data, the job set that we had in income and satisfaction, and treating the satisfaction levels as equally spaced, but will midpoint of the income categories as the row scores, giving the following results. So suppose CMH test job set and the row score was assigned to 7.5, 20, 30.5 and 60. That's the midpoint of the intervals, the 4 intervals that we used, and then that will give you the test for different statistics. Say for first one is the correlation coefficient, second one that correlation coefficient that with 1 degree of freedom, then row means, then column means. This is the 2 ANOVA, then the p-value, and then the general chi-square association with 9 degrees of freedom also would be provided here. So you can see that none of them are significant, but the correlation coefficient with 1 degrees of freedom test is indicating quite closer to the significant level p-value. So now we'll see how we can generate some measures of association in R. So first start with the phi contingency coefficient. The phi contingency coefficient is actually calculated by the square root of chi-square value divided by n. If the value lies between -1 to -7, it indicates a strong negative correlation. If value lies between -7 to -3, it concludes a weak negative correlation. If the value lies between -3 to +3, it denotes very little or no correlation. If the value lies between 0.3 to 0.7, it indicates a weak positive correlation. If the value lies between 0.7 to 1, it represents a strong positive correlation. Another measure of association for a ordinal nominal data categorical data is the contingency coefficient. The observed contingency coefficient is actually C observed the chi-square by chi-square plus n, where chi-square is the chi-square statistics and n is the total sample size. The standardized contingency coefficient is derived by C observed by C max, where C max is actually fourth root of r minus 1 by r into C minus 1 by C. But if when column and row are different same, then it can be easily simplified as square root of r minus 1 by r. And C standard lies between 0 and 1. 0 indicates the independence and 1 indicates the dependence. Another very important measure of association is Camer's V. So Camer's V is a measure of association between two nominal variables giving a value between 0 and plus 1. It is also based on Pearsonian chi-square statistics and was published by Harold Kramer in 1946. And the formula is this, that minimum of V square root of phi square. Phi is the phi contingency coefficient divided by minimum of r minus 1 and C minus 1. Then these three measures that we have learned. The first measure, the phi contingency coefficient, is valid for 2 by 2 contingency tables, and other two can be applied K by L contingency tables, more general. But contingency table, if you are generating some results through the functions that I am going to talk about, if the table is 2 by 2 contingency table, then only phi coefficient would be displayed. If it is more than 2 by 2 contingency table, if it is K by L contingency table, then it won't calculate the phi coefficient, because phi coefficient is valid for 2 by 2 contingency table. So here the function that I am going to use is the ASOC stats, ASOC SSOC STATS ASOC, and I'm just GSS table that we earlier used several times, that can be passed through this function, and that function will give you the results. One side is the likelihood ratio test and the Pearsonian test, and then it would also provide the three different coefficients that we learned about just in last few slides. The phi coefficient is not available because we have seen the GSS table is not at all a 2 by 2 contingency table, but it can calculate the contingency coefficient. Is more general measure of phi coefficient, and then Kramer's V is both showing 0.085 and 0.084 are very weak association. It's not very strong association at all. There is another measure is actually Goodman-Kruskal gamma, which is more suitable for a ordinal data. So far that the three different measures that, as you know, that are valid for nominal data, but for when ordinal data is there, it gives you some other advantage, because ordinal data has some order. So you can use more robust measure here. And so Goodman-Kruskal gamma statistics based on a comparison of concordance and discordance pairs of observations in the case form equivalent to two-way table. So Goodman-Kruskal's gamma is a measure of rank correlations actually, that is similarity of ordering of data when ranked by each of the quantities. It measures the strength of association of cross-tabulated data when both variables are measured at the ordinal level. It makes no adjustment for either table size or tiles. The values ranges from -1 to +1, that is 100% negative association and 100% positive association for one, that is perfect agreement and perfect inverse disagreement. For -1 it is perfect disagreement, for +1 perfect agreement. So says job set is one of the data that has the that is the ordinal factors available, where the table was created by 2 ordinal factors. So that can be passed through gk gamma function, the job set. It will give you the gamma value, which is 0.221, which is of course positive association but not very strong. And the confidence interval also given, that is -0.9 to 0.451. This is not at all significant. Now we'll move to measure of agreement. The kappa function in BCD package calculates the Cohen's kappa and the weighted kappa for square 2A table with the same row and column categories. That Cohen 1960. Normal theory Z tests are obtained by dividing kappa by its asymptotic standard error. A confident conf-int function method for kappa objects provides a confidence intervals, and kappa lies between 0 and 1. 0 means no agreement and 1 means perfect agreement. So kappa function can be, say, the sexual fun function data can be used here. Just pass to the kappa k is uppercase kappa. So pass kappa with the sexual fun data within kappa function, then it will give you the measure of agreements, unweighted and weighted. The values are given and p values are also given, and the unweighted was not significant but weighted values are showing significant, but kappa values is 0.23. So the positive association agreement is there but little weak agreement. And one can also display by a plot that is called agreement plot. Agreement plot can be used just within agreement plot. You can pass the sexual fun data and main equals to is sex fun. Then you will see the display here. X axis would be the wife and y axis considered as the husband, and the 4 different choices are never, fairly often, very fun, always fun, never fun, fairly often, very often, and then very often, and then always fun for husband. And then you will have the when the shaded box are above and below the diagonal red line that is displayed, is actually indicating a lack of exact agreement can be attributed. So that's if you see the always fun, both husband and wife are telling it is always fun actually, because it's completely on the middle line. So up and below, above and below of the red lines area are almost same. Similarly for very often and very often also it's showing almost same, but other two, if you can see that actually the most of the area is above the red line, so it's indicating the lack of disagreement here, agreement here. So it's showing some disagreement between first 2 categories. Next perhaps the last one is the correspondence analysis. The correspondence analysis, CA, is a multivariate statistical technique which is conceptually similar to the principal component analysis but applies to the categorical rather than continuous data. In a similar manner to principal component analysis, it provides a means of displaying or summarizing a set of data in 2-dimensional graphical form. All data should be non-negative and same scale for CA to be applied, and the method treats rows and columns equivalently. It is traditionally applied to a contingency table. The CA decomposes the chi-square statistics associated with this table into a orthogonal factors. Because CA is a descriptive technique, it can be applied to table whether or not the chi-square statistics is appropriate. So use the CA package for correspondence analysis for visually exploring the relationship between rows and columns in a contingency table. Here we carry out the simple correspondence analysis of the hair eye data. The printed results show that nearly 99% of the association between hair color and eye color can be accounted for in 2 dimensions, of which the first dimensions accounts 99%. First dimension accounts for 90%. If you see the results, you can just CA and pass the table here I, and you will get the results, the eigenvalues and the corresponding mass, chi-square distance, interior dimension 1 and dimension 2, and this way you will get all the informations. And then finally, if you need the plot, and then you can use that plot and CA object, pass the CA object within the plot, that will give you the plot. It can be seen that the most of the association is accounted for by the ordering of both hair color and eye color along dimension 1, a dark light dimensions. This is all about the contingency table analysis. I'll stop here, but there are a lot more for categorical data analysis that can be covered some other time. So in this module we have learned the measure of association for a contingency table analysis, rather for a categorical variables, what are the different measures of associations, what is the measure of agreement, what is the correspondence analysis. These are the few things, the inferential aspects of the contingency table, and we have learned through these presentations, and hope this will be very useful for a preliminary exploration of any categorical data.